Hello, everyone. Thank you for having me at ODSC West 2021. My name is Luis Ceze. I'm a co-founder and CEO at OctoML and professor of computer science and engineering at the Allen School, University of Washington. Today, we're going to be telling you about our work on making machine learning models easier to deploy with high performance on a variety of hardware targets, building on our efforts on the Apache TVM project and our OctoML platform. So the motivation for work is that machine learning is hard and costly to deploy. This is for various reasons. First, it takes a lot of engineering to deploy a model. It's very cloud hungry. So if you deploy it in the cloud, use a lot of cloud resources. It's very silicon hungry. If you deploy it in the edge, it takes a lot of compute resources. And if you look at, if you zoom out and look at what we call an ML ops flow from data to deployed model in the cloud or in the edge, it's various stages, right? You do the data management, data collection, processing step. Once you select your training data, you build your model. That's the model development, training, and even model management. And then you have to prep the model to get ready for deployment. Okay, and that involves optimizing your model to make the most out of the deployed hardware because, again, machine learning is very compute intensive and memory intensive. You need to package it for deployment. Okay, and this step here has several gaps. First, there's often a performance and efficiency gap, meaning that your models tend not to be fast enough to hit your deployment targets, or if you're deploying in the edge, efficiency matters a lot because you need to make it live with the battery life available. And if you deploy it at scale in the cloud, the amount of energy that it uses can be very, very significant. I'm sure you've heard of all the issues with the environmental footprint of machine learning, and we want to make this as efficient as possible to use less energy when deployed at scale. And this step here is also largely manual, so often it takes a couple months to get a model ready to be deployed when you hand it off from data scientists to software engineers. And so it's, there's a productivity gap there. And finally, machine learning is, as we're going to talk more about in the talk here, is notoriously hard to port. Once you get a machine learning model and you get it ready for a hardware target, if you're going to move it to a different hardware target, you have to redo a lot of this work. Okay? So, and that's really what OctoML addresses. It's really this gap in performance, efficiency, performance and efficiency, productivity, and portability of machine learning. So there's various trends here that motivates our work. First, ML workload diversity is really exploding. If you follow, papers with code, you're going to see that this is a snapshot from a little, not too long ago. They already had just under 55,000 papers with code. If you just look at just semantic segmentation of images, there is, roughly 2,100 papers. Okay, so that's a lot, papers with models. Now, and the trend is accelerating. So here are a couple of plots on the number of papers with code entries over time. And this is not cumulative, by the way. This is actually non-cumulative plots. Okay, so you see that's accelerating very, very fast. Not only, paper with code with, entries, but also, data sets that accompany them. So huge workload diversity. The other trend is that machine learning capabilities in hardware is also exploding. Just take one example. If you look at Tensor Cores from NVIDIA, it has different features to support different data types in hardware. It has hardware support for sparse operations, for sparse tensors. And the reason I mention this to you is that this affects programmability quite a bit. You have to be able to get your model to map and make the most out of the hardware target. Okay, so and this really, the bottom line is that, this exploding ecosystem of hardware and software, and of this exploding ecosystem of model diversity, different frameworks in which the data scientists use to express their models, and the variety of hardware targets creates this large cross products because they have a very fast growing and evolving framework and model diversity, and you also have this Cambrian explosion of hardware targets to map your models to. So in this ML software ecosystem, it tends to be either use case specific or hardware specific. That's often handwritten. It tends to be very painful and unproductive for the users at the top, and also unsustainable for hardware platform vendors that need to support those models and keep up with framework evolution. So that's why we built Apache TVM. So we started Apache TVM about 5 years ago at the University of Washington with several collaborators. And the vision there, TVM stands for Tensor Virtual Machine, and the vision there is really to be this automated, to simplify this path from framework down to the hardware in which you deploy the model, and build this automated open source unified optimization layer that takes models as inputs and produces hardware specific native code. Okay, now we're going to dissect that because I know there was a mouthful. So what is TVM? Apache TVM is an open source project aiming to enable access to high performance machine learning anywhere on any hardware for everyone, make it easy for folks to use it. Okay, so it's quickly becoming an open industry standard. We have over 615 lifetime contributors to TVM. It's been used in production at Amazon, Facebook, Microsoft, and hardware vendors like Qualcomm, ARM, AMD, and so on. Okay, so and to keep going down here, so here's a high-level stack of TVM. So TVM ingests models written from major frameworks like PyTorch, Caffe2, CoreML, DarkNet, Keras, MXNet, and so on. So those are the models where the models, those are the frameworks in which the models can be expressed, and it gets ingested into the TVM. The TVM framework. That means that it's translated, these models are translated into a representation that we call relay. It's a high-level differentiable intermediate representation. Think of it as an abstract representation of computation involved in that model. That supports a fairly rich programming model with, control flow, different data types. You can express functions, and has primitive operations, supports typed tensors, and more. That's really the high-level data flow representation which your models are ingested into. So, and that representation is translated down to we call the tensor IR. So there's a low-level IR that represents, the operations, the kernels, that can be compiled and optimized for all supported platforms. Think of it as this is, a linear algebra intermediate representation that represents the computation in your model as, multidimensional linear algebra operations. Okay. As you flow down the stack, you can lower that representation into code gen backends supported directly in TVM that supports a wide variety of architectures from Intel x86, NVIDIA via CUDA, AMD CPUs, APUs, and GPUs, ARM CPU, M&A class, and also GPUs, and you're going to see more later supports, ARM Ethos NPUs as well, support MIPS backend, RISC-V, and even FPGAs for specialized hardware designs. Okay, so this is TVM's rack backend. So just to be clear with the path that I showed you here and repeat myself, models represented in these frameworks gets lowered from the high-level IR all the way down to a code gen for a specific hardware architecture. So that's one path. Okay, so another path is also to make use of pre-optimized operator libraries that programmers might have, the hardware vendors might have produced. For example, cuDNN, highly optimized operators for NVIDIA hardware, or you can use NVIDIA's TensorRT compiler for parts of your model, DNN library, or ROCm from AMD. And TVM can help automatically choose whether it should use existing pre-optimized libraries or if it should use its own code generation path. So we want to make the best use of this pre-optimized code as possible. And all of this is actually guided by machine learning based automation engine. So this essentially this whole process of library optimization step effectively leads to a large optimization space that has many parameters, and you want to search what's the best parameter for your model optimization. So it is all guided via machine learning based engine that collects data from all these transformations that's doing in the models and measures them to see how well they're doing, and then makes decisions on how they should be applied. Okay. So to spend a little bit more time on this, it's fairly interesting and unique. So here's basically what TVM does. Is this is part of what we call auto TVM. It's just one way of doing it. There's many evolutions of that. You can learn more and hear more about in other talks. And there are links in our website on more information about this. But basically, the way this works is the code is represented in a way that we can extract. The code for an operator is presented in a way that we can extract features from that. Think of it as memory access patterns, the length of loops and so on. And we extract features from the code, and we use that as a representation of what the code of your operator is trying to do. Okay. So now what we want to do is essentially provide several transformations in this model, in the model of the code, okay, and measure, how each one of these candidates of your variant of your code perform, and then we can pick the fastest one without running them all. Okay. The way that's done is we run experiments, different versions of this code. We measure it in the actual hardware, and then we produce a training data that allows us to build a statistical cost model that allows us to make predictions of how would that code behave if you had made different optimization decisions. So we can decide whether or not this new candidate is actually likely to be faster than your previous version or not. Okay. And what's cool about this is that since it learns by running experiments, you can adapt to new hardware and also new different types of code without having to rely on expert programmers dealing with optimizing the code by hand. Okay, so essentially then we extract hierarchical optimization search space from a naive implementation of your code, and then we can start. So this cost model that I was telling you about by running experiments doesn't have to start from scratch. You can start from an existing cost model and do a form of transfer learning, so you can get to an optimized version faster. So basically, the more it used, the better it gets. So let me show you a quick example here. So this is an example of a piece of code we optimize in this process. I think it's a 2D convolution. On the x-axis here is different trials of the code in the hardware. The y-axis is the performance relative to a hand-tuned implementation. In this case, it could be an N implementation. The dotted line here is one example of just doing what we call black box auto-tuning, randomly mutating the code and see whether it's likely to be better. It gets better over time, but doesn't quite reach the baseline. The blue line here is actually using this machine learning based auto-tuning, building the cost model and show it evolving over time. And then it's with about 100 tries or so, it already reaches hand-tuned performance, and then within about 400 trials, we already 1.5x faster. This is just one example. There are many different types of code. We can adapt this to different hardware. What's cool about this, is that if you start with an existing, cost model that might be similar enough, we can get to a cost model very, very quickly and then produce a good version right from the beginning. So this shows the power of being able to learn from prior experience. Okay, so from prior experiments. Now, anyways, I just wanted to zero in here. So this is sort of like one of the cool things about what TVM does in general. Is one example of using machine learning to optimize the code for your machine learning model. Now, how do we use TVM? So here's a very simple example of using TVM. First, you declare the shape information model definition that you're trying to do. So that's the input shape. And then in this case, we're importing the model from an Onyx model, representation. And then declares the input shape. And then we import this into Relay. Relay is this high level data flow graph IR that represents your model. So that's the first step. Then the second step, you compile and create an executor for the code to generate native code. And here we generating code for a CPU using an LLVM based code backend. And then finally, here's where you run it. Now you have the code, and you just say and execute that code with the inputs. Yeah, sure. The syntax here is a little complex, but this is abstracting a lot of work behind it. So zooming out, so why should you use Apache TVM? Let's start from the perspective of the ML end user. Okay, so that perspective is that a user wants to quickly optimize their model on their best hardware possible. Like we can help choose a hardware by trying among them all, or you want to optimize for specific hardware targets. So that's how an ML engineer would use for production apps, or you might use it for product R&D as you're trying to figure out what hardware should run it on, or even for ML researchers that are optimizing their models as they go. Okay, so that's the perspective of the ML end user. Now, from the bottom, the perspective of the hardware vendors is that what they want is if they're a hardware vendor or a cloud platform provider, they want to offer their customers the best ML software stack for all models. Okay, so the user there is a system software engineer or a technical sales demo. That what they want to do is say like, hey, you have a new hardware or a new platform, we want to show you're able to run all of these models. So what each one of these get is really this ability of getting your model to run where they want to run. From the perspective of the end user, you give choice of where your models could run, and because you can support a wide variety of hardware targets, so it gives them choice of hardware. From the perspective of the hardware vendor, if their hardware or the platform is supported in TVM, they enjoy the ability to run models written in all these frameworks and a wide variety of models that are automatically optimized for their offering. So they can offer the possibility to run all of these hardware and all these models on their hardware or platform. So how well does this perform? This is a quick overview, like very high level performance overview. So you can read much more about it or reach out if you have questions. So what I'm showing here is each bar is a different model, okay, and in various different hardwares. I'm going to show some specific examples here. So a red bar here shows a private model. This is a model that's not in the wild, so custom model from users. And the blue bar are public available models. These are models that are available in the wild because either they're popular models and models that have received probably a lot of optimization attention. So the things I wanted to notice here is that first, so look at the scale here, and we offer performance. This is log base 2 over the baseline, so log scale. And one extreme here is 34x better performance compared to the baseline on a YOLO V3 running on a MIPS-based camera platform. And then this is a public model. There's a bunch of private models. One example from one of the customers we worked with, it's a video analysis model running on NVIDIA T4, and this is compared against TensorRT. Again, in this case, it happens to be better than TensorRT because of this custom on-demand optimization of custom model, like generating customized model, specialized model for that model, for that machine learning model on T4 using our optimization techniques. So the hand tune optimizations and the hand tune support as part of that stack could do quite as well in those models, and TVM was able to do that without having to do manual optimization. So we also have the ability to support, as part of the participants in the TVM community have built support on mapping boosted trees into TVM by converting XGBoost like models into sparse tensor programs and running through the TVM flow. And in that case, we had 4x better performance on NVIDIA 1070 compared to an native XGBoost implementation. So another, a public model, MobileNet V3, 2.5x better than the baseline on an ARM A72 CPUs. So in some models we don't do as well, but keep checking back because the optimizations get better, and as I said, the more you use it, the better it gets. So these optimizations, this performance tends to also improve over time. Okay, so but I also want to zoom out here. There's a lot of possibilities here, and a lot of configuration knobs. Some of them are searched automatically via our machine learning based engine. So question here is that how do end users choose between all the possible configurations of, model definitions, different types of optimizations, or even different model versions for the same end application, for the same base model, have several model variants, different combinations of kernels, different target devices, and so on. So there's a lot of possibilities here. And now transitioning to what we're doing at OctoML, everything that I showed you so far, you can go to Apache TVM, you can go to the website, follow the tutorials, and do it yourself. It requires some level of expertise to use it. We're trying to make it as accessible as possible, but the reality is it still requires some specialized knowledge to do that, and requires some setup, and requires some additional automation to do what you want to do. So what you might want to do. So that's why we built the OctoML SaaS platform. Our goal there is to offer end users choice of where to deploy their models, automation, subsume the engineering required, even to set up, all of the infrastructure to get your models optimized and deployed, and also offer performance to make the most out of your deployed hardware. So we're building this automated platform for model optimization, benchmarking, and deployment. The way it works is it runs as a software as a service. You can take as input models written in, say, TensorFlow, PyTorch, Onyx, and so on. It's a hosted service, so there's no infrastructure needed. Given that, as I said before, TVM uses these machine learning based optimizations, it depends on data, and we proactively collect a lot of tuning data that's part of our data sets, and that can be used to offer highly tuned optimizations if you run through the service. And also support automated flexible packaging to do easy model integration of the output. So, and what this produces output is optimized model for cloud and edge hardware, so gives you portability. So portability for cost, optimization. So if you're deploying in the cloud, you want to pick the instance that gives you the highest throughput per dollar, as long as it hits your latency targets. And also for design optimizations, if you're building a system that you have to make choices of deployment hardware, you're going to be able to produce your optimized model for a variety of candidates and help you pick what's the best one, right? So what the best choice of hardware model pair. It's fully automated optimization, so it saves engineering time. Remember that I mentioned earlier in the talk that we're talking about a couple of months worth of work. We're going to cut that down to 2 hours, maybe a couple of days worth of work in the platform, but we're aiming at a very short period of time to save engineering time. And also, given that we're making the platform really easy to use, you don't need to pair expensive engineers with data scientists. So you can just have you don't very expensive, hard to find engineers with the data scientists. You would make this easy enough for folks that can build the models, also get them ready for deployment. And then finally, we offer high performance, guaranteed state-of-the-art performance, and along the way also get benchmarking. So I'm going to show you a quick demo soon, but basically show performance comparisons across different deployment choices. Let me also show how this would fit in a sort of like a generic workflow of machine learning models, right? So here on the left side, you have your models in research and development when you're doing your data engineering, your model training. So once you have your model, you put this in your repository of research and development models. And then once these models are there and you want to send them to the production engineering flow, you can ingest this into the OctoML platform, either via an API in a CI/CD process, or manually use the website. And that's where you get your model optimization, like in architecture-specific compilation. And what you get as output is this module, this model container ready to be deployed. And that's where your production models and optimized models live, and you go from there through the deployment pipeline. Okay, so let me give you a quick overview on what like the broad hardware and model architecture coverage that we have. So we support any model architecture with standard operators. There are lists available in the website. And so here's some examples of supported model architectures and available hardware targets. So model architectures, ResNet, SqueezeNet, MobileNet, GPT-2, LLCM models, SSD models, and so on, just some examples here. And then in terms of hardware, we support server CPUs like Intel Broadway, Cascade Lake, Skylake, and ARM base A class CPUs. One's available in Raspberry Pis. And remember that even if you run through those, we actually manage the edge device infrastructure for you. So there's experiments running in our edge device cloud if you use the OctoML platform. And then we also support, GPU server and edge, server, say Tesla V100, K80, and T4s, and on edge GPUs, NVIDIA, Jetson, Xavier. Also support most AWS and GCP instances. So that's what's available right now. And so in Q4, Q3, Q4 roadmap, we have models with dynamic convolution operators like RCN, fast RCNNs and Mark RCNNs, and also have support for ARM Cortex A53 and Epic Milan available. There's more coming soon and in 2022 as well. Okay, so here's a very quick demo that I have for you. So, and hopefully you sign up and try and sign up for trial, for early access program. So you log in, okay, and then once you log in, you have your dashboard of models. In this case, I have a few models had already been uploaded, like GPT-2, YOLO V3, ResNet, and so on. So that's where you see the model you uploaded. So here's how you upload a new model. Support right now Onyx and TensorFlow Lite, coming soon native TensorFlow. You upload your model. So once you upload the model, it just tells you everything you've done. It validated the model, it inferred the model inputs, and it verified the types of model inputs. And then the model has been uploaded. So this is what will appear here in the dashboard when you go and say accelerate. So, and then when you click accelerate, and you choose the engines that you want to support. So here, in terms of software stacks, we chose Onyx Runtime. When available, it's going to use Onyx Runtime as an additional acceleration engine, and then also, of course, uses TVM. Kernel trials here are the number of kernel schedules. Remember that I tell you that it's the step that explores better implementations of your models to find the optimized one. So how many trials it's going to do. Okay, so you can choose several harder targets. Here we chose 2 AWS instances and 2 GCP instances. So you add all of them. So, and then when you click accelerate, so we chose like this early stop threshold here. By the way, is that after to limit the number of trials to cut down on the tuning time. Okay, so we also have something called auto scheduler, which is a yet another way of actually extracting automatically extracting better versions of your code, okay, of your operator code. So so then once that's done, you can see that the models, the workflow executions here, the ones that are running, the ones that they're complete, and how long it took. These ones didn't take too long, and then so when they all completed, some of them could take, on the order, as I told you, hours, sometimes close a little over a day here, and so then what you get after this is all done, you get notified that the optimization was completed, and then you can look at how your model did in the with the software stack that I had chosen. Remember, Onyx Runtime and TVM, and then you can see the performance we're showing here is latency, so lower is better. And in this case, just so happens that for this model, and these harder targets, TVM did significantly better than Onyx Runtime here in this instance. Not as big of a difference in this other one, but it allows you to explore in detail what are the performance characteristics of your of the model, of the optimized model. Okay, so then once you have that, what you want to do, here the package. Now remember that I'm telling you what you want is the outputs, not just the performance analysis, but the actual package for you to go and deploy. So we support several packagings. What's available right now is Python Wheel or a .so shared library, and you can click and download the package ready to be deployed. Okay, so let's download the model. Get the model, and then you can just deploy it using your preferred deployment method. So so with that, I'd like to say huge thank you to the Apache TVM community for all the work on Apache TVM. It underpins a lot of what we do. Is a important component of our platform, and we're very, very grateful to the very active community that we have there. So with that, thank you. I'll take questions, and if you want to learn more about Apache TVM, just go to the Apache TVM website. If you want to try our platform, go to OctoML.ai and sign up to try the platform. And also want to put a call out here on the TVM Con. You hear a lot about machine learning systems. machine learning, use cases, hardware vendors, and end users. It should be really, really interesting for you to learn more. Registrations are open, they're free, and there's a really exciting lineup of talks waiting for you. Thank you, and I'd love to answer any questions now.